Good morning. Can anyone hear my voice?
Yeah, teacher.
Okay, thanks. So today I think we will start discussing about the system modeling, and then we'll move forward for the single degree freedom system, where we see the response of the structure to the very simple system called the single degree freedom. Well, before I start, let me explain you a bit about okay, I have post one file. Let me share you the screen. I think this, if you can see my screen now, is the kind of the folder that I share the handout with you. And in this folder, there is one Microsoft Word file, which I think is a link for the video. Let me open the file for you. Yeah. So I provide you the link, video link, where we have a discussion last time. And I will keep updated this video link for you every lectures that we finish. Okay, and I try to keep it updated maybe the day after we have the lecture or discussion together. Okay, for one who interested on the review on the video link or the video clip, so that you can make yourself more clear understanding with some point of my explanation. Maybe it's not clear for you at the first time. Maybe you want to repeat. That is quite easy for you now. Okay. So today we will look at the modeling. Before we get into the detail of mainly about the mathematics, we will look at the differential equations and see what's gonna be the solution. So what I expect from you is we will use the mathematics as a tool, just a tool that engineer use for understand their building, how their building really move under the loadings like the earthquake or the wind. Therefore, once you learn about the mathematics, you apply that mathematics, you obtain the solution. What you have to really understand after you obtain the solution is how it's related to your real building. Of course, I obtain X. X is my movement, and say X is my displacement at a certain four locations of my building. When I obtain the solution from the differential equations, for example, I obtain the value of X as a function of time. You can see how X move with time, change with time. What I really need to really understand is about what gonna happen with my building if the X is like this, it's like that. Therefore, you need to have a very strong connection, a strong understanding between the physical model and the mathematical model. In other hands, I would say with your actual building. So of them, actual building, mathematical models, or a physical model, of them need to be strongly related, interconnected. You obtain the mathematical solution, you really understand what your physical model is, you really understand what your actual building move, something like that. So this I would say is just one of the way that I try to make an explanation to all of you that when you have the actual building, of course, we need to really understand what this on the left hand side, right? When you have the actual building, subjected to the earthquake, for example, I want to know how this building will move under the earthquake. And to get the solution or to know how it's moved, what I have to do is to represent this building, actual building, with an equivalent physical model. Of course, there's not a unique way of thinking. There are many possibilities or many alternatives on the physical model you can see on the middle column, where you can select. I think I provide you 4 cases, but among the 4, I classify into just three types or 3 classifications of the physical models. One is A, another is B and C. The model number A, I call it the condensed model. We are talking about the physical model. Model B, I got 2 choices. One is a B1, another is B2. For B1, I call it the discrete Lambert model. And B2, I call it the discrete finite element model. And the last type of the physical model, number C, I call it generalized coordinate model. Okay, so it's 3 types of the physical model you can thinking about, you can have. Starting from the condensed model, A, okay, model number A. You see the movement of the building is well defined by X, and this X is a function of Z. Z is the height of the building as well as the time T. Therefore, with this model, I can explain how the building moves at every height, every location along the height of the building, as well as the time. You can know every movement of the building along the height of them and at any time. This is what we expect by using this physical model. The second one is B number 1. With the model, physical model B number 1, I represent the movement of my building only at a certain floor level. Along the height of the building, you see, I classify my X not a function of the Z anymore, just a function of time T. But I have many X, and I call it Xi along the height of the building. This is a discrete way of thinking. We digitize along the height of the building a certain location which we believe or we think is important. And we represent the movement of them using only those locations or those particular height of the building or floor of the building, and represented by the degree of freedoms we concern X. So obtain after you obtain the solution, you could expect that only the movement at xi will be, how to say, you would get only this information. For example, the movement of floor number number 1 is x number 1. Floor number 3 is x number 3. So after you obtain the solution of this building movement under the earthquake, what you can expect is you will know what is the movement of the floor number 1, floor number 2, number 3, number 4, but you don't really know how it's moved along the height between floor number 2 and number 3. The movement of your building between floor number 4, number 5, something like this. I cannot know because my degree of freedom is not describe the movement in between the floor. I only know the movement at the floor level in this case. Okay. And sometimes some engineer would like to approximate, how to say, with a certain degree of approximation, they would like to reduce the number of X, the number of unknowns to get the metric to be smaller so that they can solve the system easier. In such a case, some people just represent the movement of the building using xi for floor number 1, and then there's the floor number 5, number 10, number 15, number 20, number 25, number 30, something like this. Every 5 floors, they use 1 degree freedom to represent the movement only. So in between, we will not know how it's moved. Okay? Something like this. For the discrete Lambda system, the third one is the B number 2. We call it the discrete finite element model. With this finite element model, I believe is maybe all of you are already familiar with the concept of the finite element. They try to represent the structures by a lot of a large number or a large number, how to say, a large number of the small elements connected together, right? Like in the building, we try to build up this model by adding columns to the beams, element of columns, element of beam, element of slab, element of shear core, something like this, right? So you building up the building in this finite element model by using a large number of elements. And for each element, I believe at the end of them, you have some node, right? You call it at the end, you call your element as a node, how to say, node information. You have the node to connect one element to another element. At each node, you will define the degree of freedoms. And the same thing for the static analysis with dynamic analysis. The same degree of freedoms are defined for this discrete finite element model as well. So I think you can imagine if you connect the columns of floor number 4 to the column of floor number 5 at the interface, the joint that connect these 2 elements together, you will describe how this joint or this node information move, and we call this degree of freedoms. And generally in the 3-dimensional model for each node, the degree of freedom is 6. We are talking about the movement of each node. degree freedoms, which is normally described by the movement along the X, along the Y, along the Z, and the rotations allow the X, allow the Y axis, and allow the vertical Z axis. So in total, normally it's 6 degree freedom, right? For each, in this figure, you can see my red color, the dot, the red dot. And if that is represented by the node information, for each node information is your degree freedoms. So you have many X. And this X is digitized into many numbers in your building model. It depends how small or how large of your element you adopt. If you use a very small element could connect together, so to build one building, you need to connect a lot of small elements, and that will bring up you to have a very large number of degree freedoms. Okay, so this degree freedom of X is defined using the same definition from the static analysis. When you use a finite element, the same degree freedoms. The last one is the number 4 is the generalized coordinate model. This model, we define the movement of the building exactly the same with the continuous model. Okay, where the X are the movement of your buildings or your structures are defined as the function of the Z, the height of the building, and the time T. But I do have some conditions imposed on these definitions of my X, which quite different from the first model, from the condensed model. With the generalized coordinate model, I have a big assumption. An assumption is saying that even though I define my X as the function of Z and time T, exactly the same way of the continuous model, which is very general, right? But I impose the assumption that my X, which a function of Z and time T, can be represented by the separation of variable. If you have learned something about the technique used to solve the partial differential equation, one of the popular technique is the separation of variable. The same thing. You see on the right-hand side of the equation show that X as a function of Z and T can be represented by a summation of Phi of Z multiplied with the Qi of T. This is just a big assumption, but this assumption is quite well accepted. And we normally know that for many real physical system or real mechanical system, the separation of variables work quite well. That's why this is another way that engineer try to represent the physical model. Okay, I will focus. I think Dr. Chatpan will talk with you about the continuous model number A and maybe number C. Yeah, not maybe. I believe he will. A and C. And B2 and B1, where the number of X is not only 1, it's 2, 3, or 4 when you have multi-degree freedom system. With me, we will start with only a physical model B. And with only 1 degree of freedom. That's what we call the first few chapters as the single degree freedom system. Okay, when we look at the physical model like A, you see the mass of model A is just the distributed mass as well. It's the mass as a function of C at the height of the building. For the B number one, this model, the mass is lumped into a spot like the red color that I shared for you. So we lumped the mass on each floor and compute what is your floor mass and the half weight of the columns and wall above and the half weight of the column and walls beneath of this particular floor. I will lump into the big mass MI. Okay, so you have M number one, number two, number three, number four. It depends on the index I that you use. For the finite element model, that's called the consistent mass. This mass metric is more, how do you say, sophisticated. It's quite complicated to explain what is the mass and the rotational inertia that explain how the element has the mass at the node that transform the mass distribution in the element into the node locations. So at every let's dot, you will have the mass. Okay, and that mass have the mass along the x direction, along the y, along the vertical direction, and also the rotational inertia or the rotational mass they call. It's quite complicated mass system in this model, finite element model. And for the last one, this one is the same. The mass is the mass distribution along the height of building, exactly the same way of modeling of the coordinate system. Look at the last column. If you use the coordinate model, you will end up with the equations of motion as in equation A. And if you look at equation A, you will see that the governing equations of your building under the force or under the earthquake is described by a partial differential equation, second order. Solving those equations, I think, is maybe your discussion with Dr. Chatpan. Number B is the discrete model, and both lump mass and finite element, you will end up with the second order ordinary differential equations as in equation B. And C, if you use a generalized coordinate model, you will end up with different type of the mathematical model, but it's look to be the second order ordinary differential equations. It's very similar to the equation B, except some parameter is well defined according to the generalized coordinate concept. Let's say M star, C star, K star, F star, something like that. Okay. So I think if you have the building, what you have to do is to first consider what type of the physical model you should apply for your case. But I do believe if your building is like a high-rise building, most of the time you will use B number 2. If your your structure is a bridge, a long span bridge, I believe the popular or is the most of engineers will use the B number 2 as well. So in almost every application, I do believe the model number B2 is very popular and quite accurate, very accurate. Compare with the Connaughton model or compare with the generalized coordinate model or even the discrete lump mass model. And it's quite easy right now since we have a very powerful computer. Therefore, you can focus on this B2 most of the time. But for a certain application, for example, if I do the analysis of the water tank, is a tower like this. Like a transmission line, any truss structure tower, or even in this case, maybe I call it a water tank on top. You have the water. Solving this by the finite element model is okay, no problem. But it's much simpler if you use just the lump mass model. Only 1 degree freedom that most of the engineer we consider at the middle of the water tank, how it's moved with time. And if I know the movement at that location, I can design my steel truss very effectively. So using only 1 degree freedom may be much simpler comparing with the engineer who use a sophisticated finite element model. But this type of the structure or some other type of structure, I can show you some example, is exceptional. Just an exceptional. Most of the time, we're talking about the building, we're talking about the bridge, or we're talking about the common structure. Those of them are very effectively be modeled by the finite element, I believe. Okay. But why today we will not learn the finite element modeling? We learn about the single degree freedom system. I think I already discussed this with you before. We learned that because number one, the solution we obtain from the finite element model, we don't know whether it's correct or not. Of course, we do believe that we model this structure very accurately. We do a very good modeling in the computer. It should be nothing wrong with that. Even though we know that we input the force, we input the earthquake to that structure accurately. It should be nothing wrong or incorrect. Then we just press the executions. And we let the software to do the solving this second order differential equation for us, do everything for us, and just return the solution to us. And who will know this is good or bad? That's why we will use a single degree freedom system to recheck the solution, to at least consider the order of the movement, order of the base shear force, and the moment with it, whether it's making sense or not, or is so large that is nonsense, is impossible. We use a single degree freedom system to do that for you. Second is, the design of the building sometimes need the what they call the deep understanding or what they call the insight understanding of the building behavior. If I use a finite element model, of course, I can test with by changing the stiffness, by changing the column to be larger, smaller. I reduce the mass of my building to be lighter or heavier. I changing the damping of my building by adding some damper here or adding the damper there in my computer model and see the result and compare. It's possible. It takes so much time, believe me. You will spend a lot of time for that. It's a kind of the type of the trial and error analysis. But with the single degree freedom system, it's quite easy. You will learn. You will know that effect of the increasing the stiffness of the system gonna be good or bad for you, for your case, for your building, for your structure. You're gonna know in a very short time if you want to change the effect of the mass. It will be positive or negative on your solutions. Even you will modify the damping, you will see the result. You change the loading, you see everything go very fast, spend very short of time, short period of time to do the analysis. That's why it's very helpful, in other words, for us to have the single degree freedom in hand. The knowledge of that will help us a lot on checking the finite element result, as well as help us to have a clear understanding of the behavior of your structure or your case or your problems, as well as maybe provide you some more insight so that as an engineer, you can, as a designer, you can provide the effective solution for your case. Okay, that's why we will start with the single degree freedom system now. Let me move to the next slide. It should be this one. Oh, no, sorry. Chapter 2. Okay. Let me continue on the chapter 2, where I think the single degree freedom system will, how to say, explain and discuss with you. I will move to the point I believe that I will no need to cover there. Okay, let's see here. Okay, before we start, let's do this together. See, in the figure, if you have the building, real building, you try to represent this real building by a certain type of the physical model. In this case, I select the lump mass concept to perform the physical model, okay? Even though the building has, I don't know how many floors it has, but for sure, I think the floor number is more than 60 or something like that. And I represent this twin tower by only one, how to say, 5 degree of freedom only. If you can follow me, I would say, okay, I have X number 1 here, I have X number 2 here. All of them is a function of time t, okay? Number 4 and number 5. I usually 5 degree of freedom to explain this tall building twin tower. If the height of the building here is h, I do believe that floor number 5 of mine is the roof of them, the same height. Okay. And see, the mass is lumped. Maybe the mass here, from here to there, we lump to M1. And the mass there to there, maybe I lumped into M2. And this is here, and that is there. Something like this. You lump the mass, you lump the stiffness. For the stiffness, it look like you cut the building. You cut the building, for example, along the, let me say H number 1 here. I'm sorry. For only the portion of the building called H number 1, if I model the building in the finite element, I don't know, you have the many floor there, you have the column, you have the beam, maybe. And if I assume that this is fixed like this is H number 1, and apply the force F. And then this portion of the building we move with delta. My K number 1 is defined by my F number 1 over delta number 1, something like this. So I do this for every portion of the building and represent them by just the 5 degree of freedom system called the lump mass physical model. Represent the mass by M1 till M5. Represent the stiffness by K1 till K5. Like this. However, if I would like to represent this building by another physical model called as SDOF, single degree freedom system, I will do with only 1 degree freedom, maybe here, X, just X or X number 1, only 1 X. And the mass of the building, of the whole building, we lump to the top. But for sure, if the building mass, the overall building mass, something like M total, MT, I do believe it's, of course, M is something like 1 over theta MT. We explain, I will explain this to you later, but for sure the mass of the single degree freedom system, we take only a certain portion of the mass of the building, the total mass of the building, not all of them. Okay, it's not half, it's only 1/3 or something around this. We will learn about this later if you have the, if we have some time, I will explain that to you. How about the stiffness? Stiffness K is very simple, right? You apply the, let me do this for you. Apply the force here and in the finite element model, okay? And if we move with the delta, so the K is F over delta. Something like this. Okay. So once you have the single degree freedoms, now we will try to solve this and let's see how it behaves under the loadings, many types of loadings. The system have the many degree freedom like this. 5 degree freedom is one of the parts of a multi-degree freedom system. You will learn about this later. But let's consider focus on the single degree freedom system where we'll start from today. The bridge as well. You can represent the bridge, actual bridge by a single degree freedom system as well. It's not so difficult, right? The idea is maybe quite the same with the tall building, in which you represent the mass, you represent the stiffness, and have the physical model like big M and big K like that. The single leaky freedom system can have many types, right? Like the one I show you in these figures. But in many textbooks, I do believe for the building, you have choice number 1. You can often see number 2, and you quite often see number 3. For the tall buildings, most of the time we use either number 1 or number 2 or number 3. But all of them should provide you the same solution. No matter which model look like, they will share the same mathematical models, and of course, they will share the same solution of X. So that's why in the following example, no matter I use the spring mass system like this, you see like this one, or I use number 1, or I use number 2, it's no difference. You could treat they are the same, even though it look different. However, some engineers prefer to use number 1 if they feel that the building is something like the movement is controlled by fractal mode. And use number 2 if they believe that your actual building, the movement is controlled by the shear mode. Number 3, they don't care. No matter your movement is controlled by the fractal mode or shear mode. Just the spring, represented by the spring. Number 3. Okay. But believe me, all of them, the same mathematical model. You end up with the same mathematical model, and with the same mathematical model, you can expect the same solution of X. No difference. So let me discuss with you through just only the spring mass model, because in many textbooks, they use spring mass model quite often. We use the same. To write down the equations of motion, what you have to do, in fact, is you just represent, okay, you have the spring parameter is K, you have the damping C, and you have the mass M, okay? And under the loading, maybe I would like to say, it should be there is the force. Normally, there is a force of time T like this, acting on the mass. But in this one, we just show you what they call the free vibration. If you have learned the differential equation before, you will know this is a homogeneous system. The system where there's no the right hand side, right? No, the right hand side is 0, something like that. Okay, let me draw you one more thing called the velocity. If X is the displacement, the velocity X dot will be used. And since this problem is about the second order differential equation, X double dot is the accelerations. So the X displacement, the X dot and X double dot, the positive direction is moved to the right hand side. We define like this. And once you define the degree freedom like this, let's do with the force equilibrium by just cutting. I cut the spring, I cut the dashpot. Oh, this one is this is spring, right? You know, but this one is called the dashpot. It's called the dash and pot because of this. You see, it's the dash, it's the pot, something like this. And this is the damper. It's the symbol for the damping. Okay. And the name is dashpot. We often call it dashpot. If I cut the spring and the dashpot, what I have to do, I would get something like this, right? The kx, the force. The direction is, if your x is moved to the right-hand side, then the kx, the spring try to bring the mass back to the zero position. The same thing with the damping. This one is quite difficult to imagine, but I try to explain you. If you cut the dashpot, assume that now the building or the mass try to move to the right-hand side. Remember your x dot, the velocity positive is to the right-hand side. Therefore, there is a force, internal force. When I cut the dashpot, they try to bring the mass back in this direction to the left-hand side. I often explain this to my student. Imagine how this damping force look like. Please imagine like this. If you dip your finger, put your finger deep into the water, and if you move your finger in the water, you will feel some resistant force from the water acting on your finger. And this force, resistant force from the water on your finger, it will very large if you move your finger with a very, very fast speed. But if you slowly move your finger into the water, and if you move to 1 meter, 2 meter, 4 meters, or 1 kilometer, it's not affect the force. The displacement is not affect on the resistance force on my finger. The only parameter that I concern is the velocity. It depends. The amount of force on my finger will be small or large. It depends on the velocity. If I move my finger very slow, I will feel very small force. If I move my finger with a very, very high speed, I will feel very large force. I think you can imagine this. So this amount of force is proportion to the velocity term. In other words, that resistant force, I call it R, will be a function of x dot. Okay? And it equal to, let me go back. Oh, I'm sorry, it's 11:20 already. Is the constant, let me say C multiplied with the x dot. This is amount of force, resistant force on my finger. The same thing with the dashpot. How about the direction? The directions, what I feel for my finger is, it will acting on my finger in the opposite direction to the velocity. If you move your finger from left to right with velocity like this, you will feel some acting force on the opposite direction that will try to break my finger. Okay? So the same thing, if you assume this mass is moved under the water, the dashpot will do the same thing on you with the mass in the water. If the mass is moved from the left to the right, this is a positive direction for the x dot, right? They move from left to right. Therefore, this will be the resistance from the water try to stop the movement of my mass by putting the force in the opposite direction of the velocity. That's why I can write down my Cx dot in this direction. the arrow from the right to the left, like this one. And if I assume my force here is 0, no external force, just the movement of the mass and the spring dashpot themselves. From the second law of motion of from Newton, right? Law of motions. Summation F equal to MA. You can have something like this, right? Minus CX dot, since if the force, the arrow go to the light is positive, therefore the KX and CX is all negative, right? So summation of F is minus CX dot minus KX equal to MA. A is the acceleration of the mass, is the X double dot. And if you write down this, you can obtain equation number 1. And then if you rearrange the form, move every terms to the right-hand side, and let it equal to 0, is obtain equation motion as in equation number 2. Write it. Okay. So you obtain already now the equation of motion. And this is a second order differential equations, which contain X double dot. You see, mx double dot plus cx dot plus kx equal to 0. The one of the motion system that we should discuss in the very beginning is about the vertical system, in which this system has the special thing in which you have the gravity of the earth acting on them if they would like to move along the vertical directions, and the effect of the gravity will go something like this, right? And you can derive this by yourself, not so difficult, but I do believe many of us prefer to remove this term out from their consideration, and you see finally you already obtain the same thing, the same equation as in equation number 2. You see number 3 and number 2, they are exactly the same, except from number 2, I think the 0 position is like this, right? You have the 0 position and you move back and forth, allow the 0 position here. But for the vertical system, you should imagine that before you start to move the mass, due to the gravity, the mass will go to this level. Let me do this. Let me draw a little bit different. From the center of the mass, from here to there, you already have the X bar here. This is X bar. So the movement of your mass is not 0, it's X bar here, and you have the vibration up and down, allow the X bar position, not 0 position, because the 0 position is here, right? Yeah, that's it. So once you obtain the X, you just add X bar into, and that's gonna be the absolute motion, the total motion of your building. That's it. But in terms of mathematics, we prefer number 3 because it is exactly the same with number 2 and it's easy to deal with. The last one is a pendulum. The pendulum is the movement is the swing like this, right? Okay, back and forth, back and forth. In our system, civil engineering system, it's very rare case that we have the swing problems in our structure, civil engineering structure. Most of the time we have vertical and horizontal, but not the rotation like this. But you can expect that your friend in mechanical engineers, they have a lot of problems dealing with the pendulum motion like this in their machine, in their motors, in their, how to say, rotational machine or equipment. However, let's see, it's not so difficult. If you would like to have the physical model to represent the pendulum motion type of your structure, you do the same thing like this, right? Like a summation if along the radian equal to MA. So you got the T, I'm sorry, this one, you should change to theta. It's not, and theta is a function of time T, okay? T minus the mg cosine equal to 0. Oh, I'm sorry. Oh yeah, that's good. And the along the tangential relation, summation f tan equal to ma, you obtain the minus mg sine theta minus cl theta dot equal to ml theta double dot. And the equation of motion becomes something like this. And believe me, this one is not easy to be solved. It's a nonlinear equations. When it's become a nonlinear equation, it's very difficult to be solved. Many times we do the linear analysis only. So it's quite often that the engineer will assume something like this. They expand the sine theta term like this and just use the small vibrations. Assume that the vibration is very, very small, and then we end up with another equation. If this one, equation number 4 is nonlinear, number 5 is the linear equation. Okay. Okay, I would like to stop here, and the thing so far is to explain you how we represent the actual building or structure by a physical model. And from that physical model, we know that we will represent it by the mathematical model, and we will solve the mathematical model to obtain the solution and relate back to the physical model and the actual model, how it's moved with time. However, in the very first chapter, we will learn earlier the single degree freedom system. So I will discuss about only this system with you, where the system we have only one mass, only one parameter of the stiffness K, and only one parameter of the damping C. And with this type of the single degree freedom structure or this type of the physical model, we end up with the equation of motion like in equation number 2, number 3, and number 5. Of them, the second ordinary differential equations, second order ordinary differential equations. And next time we will try to solve them, how to obtain the solution of X under various type of loading. Okay, I would like to stop the discussion today here. And if one of you have questions, this is the time. No? Any questions that you have?
ถามเป็นภาษาไทยได้ไหมครับอาจารย์
I prefer English. You can try not with English, please.
Can you explain behavior of
Very good.
that point again?
Which point?
That's
Amen.
points in horizontal motion system.
Horizontal motion system. Explain what?
Dashpot.
The dashpot.
CX.
CX. Okay.
Can you explain again?
Yeah. In very short is I ask you to imagine put your finger into the water, right? And you should imagine how large or how small the force by move your finger into the water. If you move your finger into the water with very, very slow speed for 1 kilometer, for example, you will feel nothing. If I allow you to move in the sea, you put the water and you just walk very slow walking into the water, nothing acting on your finger because your movement, your walking is very slow. No force, very small force. But on the other hand, if I ask you to put your finger on this in the sea by sitting on the board, speedboard, the boat is running with a high speed. If you dip your hand finger into the sea, what can happen? You can imagine, right? It's going to be very, very large force, resistant force from the water, from the sea acting on your finger. This explains that the resistant force in the water is proportion or dependent on the velocity of your finger. The same thing with the x dot here. That's why I put the absolute R is the function, is a proportion to the x dot and can be represented by a c multiplied with the x dot. This explains only the amount of force. But when you would like to see the direction or to imagine about the direction, you have to close your eye and feel it again. If you put your finger into the water, when you move the finger with the speed positive, right, from the left to the right, you will feel the resistance from the water acting on your finger in the direction from right to left. Try to stop your movement. The damping CX dot always try to stop the movement. So in this example, I define the movement X dot to the right-hand side. Therefore, they try to stop. They try to make my velocity to be 0. The force must be on the in the opposite direction. That's why you see the arrow of the CX term be the vector like this, right? To the from the right to the left, they try to stop the motion. I don't know this. I repeat my explanation, but I don't know whether you understand about this or not. It's okay?
Oh, okay, teacher. Thank you.
Yeah, welcome. Any other question? Oh, if you don't have, I'm sorry, I'm really sorry for this coming Thursday. It seemed like this morning I get the call from Department of Highway would like me to join the meeting with the Thailand and Laos Friendship Bridge over the Mekong River on Thursday morning. And I'm afraid that I cannot finish that meeting before the class. Can we do it with this? I think I have the lecture with a video clip with from last year or last year lecture. I will post that video clip for you this coming Thursday, okay? And if at the end of, and I will go next chapter after the video clip for the next Tuesday, sorry. And please, how to say, help me by watching this video clip for this coming Thursday, and I will provide you some time for the discussion if some part is not clear to you on the Tuesday, next Tuesday, okay? Sorry for that, but I try to don't to make up with you, unless at the end of the class before the examination, I mean before the midterm, you need some more explanation on certain particular issue or topics. Let me know. We can make up the time and do that with you. Okay. If you don't have any questions, I would like to stop here and hope to send the video link, this video link for today video clip to you by maybe tomorrow. And I will also provide you the video clip for the explanation from 2.2 to maybe the end of this chapter and the beginning of the next chapter, okay, by tomorrow, so that we don't have class. Okay, we don't have class on this coming Thursday. We will have a class again on next Tuesday morning. Okay, thank you. Have a good day and bye-bye.
Thank you.
Welcome. Bye.